This is the second lecture in the Control Systems Technology MENG2015 course, and in this lecture we'll be looking at Laplace transforms. The intention here is to give you a sense of how Laplace transforms are used for controls and be able to use them comfortably. I'm interested in being able to use the Laplace transforms to support the modeling of systems, so we can do the control system design, right? So it's a particular application. Once you can do that, you'll be good. So Laplace transforms, and I don't know if this really was really clear from what you did before, but Laplace transforms are useful because it allows us to describe physical systems that are governed by differential equations by using that single operator instead of trying to solve, differential equations or systems of differential equations to determine the behavior of systems. So we describe physical systems, and almost all our systems come down to differential equations, right? So whether it's thermal systems or whether it's electrical systems or mechanical, all of them, when you get down to what are the governing equations of different physical phenomenon in our different types of systems that we have, fluid dynamics, they're ultimately governed by a system of partial differential equations called the Newton-Raphson equations. So that's what governs kind of like the movement of fluids in pipes and that sort of thing. So any system you want to pick up and look at, you'll probably come down to finding that the governing equations are differential equations. These can sometimes be difficult to manipulate and solve. So if you have a complex system of differential equations, then they can be hard to manipulate and solve in their raw form, in the time form. So what Laplace transforms allows us to do is to convert our system of differential equations to an algebraic form using the S operator. Right? And so now we have a system of ordinary differential equations still, but it's algebraic and it's not much easier to manipulate. And it allows for different systems, different types of systems to be modeled in a common domain. So we can take our electrical system and our mechanical system and we can put them together and we can deal with it as one integrated system in S, as opposed to a current as a function of time and then a motion as a function of time, etc. So it does allow simpler manipulation. So the solution of an ordinary differential equation is difficult, so what we do is we transform that differential equation into a domain where the solution is easier, we solve the problem, and then we can put it back out into the time domain, if you like, and do the inverse transform to move it back into the original, in this case, time domain. And this is a little diagram which represents that. On the sort of top half of the diagram above this dashed line is the time domain. On the bottom half is the Laplace domain. So we start here where we have an input and we have a system which is described by a set of ordinary differential equations, and that's going to, when a known input u is applied to the system, it's going to generate an unknown output y, and we'd like to know what that output is going to be. So we can either get from our input to our output by solving our ordinary differential equation, and we just said that's difficult, or we could do our trick, which is that we do a transform from the time domain into the Laplace domain, and so we're now expressing our ordinary differential equations as algebraic equations in Laplace. So to do that, we have to transform our input into an equivalent Laplace domain input. But we also, and this is the more tricky bit, we have to transform our system, describe our ordinary differential equations, into a system described by algebraic equations, which we call a transfer function. So now our input in S goes into our transfer function, which is also in S, giving us, of course, an output in S, which is y as a function of S. But now, instead of having to get from input to output by solving an ODE, you get from an input to an output by multiplication. Now, the only problem is our output is expressed in S, and that's not what we want, so we have to then do an inverse Laplace transform of our output to get our output back into the time domain, which is what we're interested in. So, you know, this is a tricky route, this is a longer route, but it allows us to do simpler maths to get back to where we want to go. All right, so, and this should be pretty much clear to everybody, I think. But this is our Laplace transform. This is the core equation. So to get our function in S, this is our function here. To get this function in S, which we're looking for, say, you know, we have to do this, we have to transform our system from, as say this is f of t, we have to get it in f of s. We're also transforming our input to u of s. Right, so to get f of s, what we do is we apply our Laplace transform. Right, we're applying our Laplace transform to our function in t. And how do we do that? We take our function in t and we multiply it by this baby. And this is called our Laplace operator. E to the minus st. So now we see this s comes in, right? This is where our s comes from. We multiply our function by the operator e to the minus st and then integrate it between 0 and infinity over time. Our function in time is defined for all time greater than 0, but it's 0 for all time less than 0. Right, so this runs from 0 to infinite time, so we're integrating over that range. Now, this is important that you need to know your, well, have access to your Laplace transform tables, which you can use. I'm assuming as well you're probably familiar with this. You're given this in your exam papers and all the rest of it, so I make this readily available because you do need to use it. And on the left-hand column, you'll see Laplace transform, the f of s version. On the right-hand side, you'll see the time function, which is in time, of course. So we'll be transforming in both directions on this. Okay, so there are some important ones here. Like, for instance, if we have a unit impulse function, Dirac delta, which is one of our important test inputs, that transforms to just a simple 1. A unit step input function transforms to 1 upon s. A ramp transforms to 1 upon s squared. T to the n, anything raised with an integer exponent power, then that gives us n factorial over s to the n plus 1, right? So that's basically, you know, as we go, that means if you have sort of a parabolic input as opposed to, say, a unit ramp input, a parabolic input will give us this equation. So if it's t squared is our input, then we're going to end up with 2 times 1, which is 2, over s to the power of n plus 1, which is 3. So you're going to end up with 2 upon s cubed, for instance. This next one here, very, very important. E to the minus alpha t. This is an exponential, a decaying exponential term, gives us 1 upon s alpha, etc., etc. So this has, you know, in this table we have a lot of more complex functions as well. Some of these will come to later in the course, like this one here. This is a very important one. This is the second order response or second order dynamics expression. If you haven't come across it yet in vibrations, you will very soon, right? This is a third order response. This looks like an incredibly complex equation, but it does actually describe the time response you get from a second order system. So this is a Laplace transform See if I can write it properly. This is the inverse Right, so this is going back to time. So if you want to get your time function, you have to take the inverse Laplace transform of your s function. So this corresponds to this part here, right? All right, let's go through some common Laplace transforms here. First one, very important, like I said, this is like a standard input, is our step input. And what we see here, in case you're not seeing it clearly, this is, oh dear, bad drawing. I don't have a ruler on this. Okay, so this is your input here, straighter than my line would indicate. So let me rub that off again. All right, so now what's the u of t equals 1, right? Because it's just 1 for all time greater than. Remember that we're defining here that a part of our Laplace transform is that we are saying that our function of t is for all time greater than or equal to 0, right? So in that case, all time greater than or equal to 0, ut is 1. So this makes a pretty straightforward Laplace transform because we just substitute in our equation from here, our f of t just becomes 1, right? So then what we're doing is actually integrating between 0 and infinity e to the minus st dt. If you remember general rule of integration, if you integrate between 0 and infinity of e to the a t dt, then that's going to give us 1 upon a e to the a t, 0 and infinity, right? So all we're doing here is just replacing our a with the minus s. So we end up with this as a constant at the front, minus 1 upon s times e to the minus st between 0 and infinity. Right? Now, if we integrate, if we apply the limits here of 0 and infinity to our exponential term, we have e to the minus infinity, sorry, minus s infinity minus e to the minus s times 0, right? E to the 0 is 1. E to the minus s infinity, well, e to the infinity is 0. Right, so our minus 1 upon s, constant on the outside the brackets there, times 0 minus 1 minus 1, that's how we get our 1 upon s. The negative disappears, right? So that's that one. Level that out. This is our one-sided exponential now. So basically we have a decaying exponential. And why are we interested particularly in an exponential term, and particularly a decaying exponential? What's so significant about a decaying exponential? Well, it's very frequently used in controls. because it provides the transient component of a control action. It's a common feature, a decaying exponential. So we see that the time function here is some constant u times e to the minus at. Right? This is the time function. So as time increases, then this becomes increasingly negative. And if the exponential has a negative, increasingly large negative coefficient, then it becomes very small, because we know that e, to the minus infinity equals 0. So as time goes to infinity, then e goes to 0. So if we evaluate e to the minus st as time goes to infinity, that's equals 0, right? And you can see here, this is exactly what happens. As time increases, this is the exponential that we're dealing with, the function, the time function, starts at 1. So in other words, our us of t equals 1, which is this part here, just giving that a simple value of 1. And as time increases, this thing just decays, becomes smaller in value. As time goes to infinity, it gets to 0. Right? That's a very important, that decaying exponential is very important in controls, because anytime you get a transient function, it's going to have a decaying exponential in it. This is our function. If we integrate this up, or take the Laplace transform rather, then we can see here f of s is going to be the integral of our time function e to the minus at times our operator e to the minus st dt, which is, so this is our f of t. This is our Laplace operator here, right? So we multiply them together times dt. Now that equals e to the minus a plus s. When you multiply two exponents and you can add the coefficients, by substitution we could very easily see that this integral now is exactly the same as what we did up here, right? But now instead of just s, you've got s plus a, right? So then it comes out as 1 over s plus a as being that integral. In case anybody wants a bit of assistance with their Laplace transforms, our input u of t is 1, because for all of time greater than or equal to 0. So as soon as time goes to 0, the value of this function goes to 1, and it stays at 1 for infinity. If we take the Laplace transforms of this function ut, this would be capital U s equals, if we take the Laplace transform, that's the parent sign, Laplace transform of u of t, that will give us integral between 0 and infinity of our function ut times our Laplace operator, right, e to the minus st, integrated with respect to time between 0 and infinity time. Right, so now we're going to substitute, make a substitution and say u equals minus st. This is, I shouldn't use u actually, let me use v, because we already have the function called u, so that's going to confuse things. So if we differentiate v, we have minus s dt. So we could say, let's do it this way, dt equals minus 1 upon s dv. Right, so now if we substitute this back in here, then we can say u of s equals integral between 0 and infinity minus 1 upon s e to the minus v dv. This is just a constant, so this can actually come outside. So I'm going to rewrite it, right? And then if we integrate e to the minus v, the integral of e to the minus v is actually e to the minus v, right? So that doesn't change when you're integrating with respect to dv. So you end up with e to the minus v. Now v is minus st, so we substitute that back. And we integrate from 0 to infinity. And if we take e to the minus s times 0, e to the 0 is always going to be 1. If we take e to the minus infinity, if we substitute in the upper limit, then e to the minus infinity is always going to be 0. So that means we cancel out the negative on our 1 upon s, because inside this bracket we get a minus 1 times minus 1 upon s is 1 upon s. Alright, so just again to confirm that's how our Laplace substitution works, and that we've shown that this function, the unit step input of a value 1 is 1 upon s. Right, and so let's move on to our next one. So the next one up we have the impulse function. So this is another, remember we're looking at these functions because these are common inputs to a system, and we could basically test a control system with an input. So we, with a step input, we test it to see how the system responds. When we apply a step input, we could apply an impulse as well. This is an impulse. Now, the rule for this is slightly different because you can see that our f of s, our Laplace form of our impulse could actually approximate to the time domain integral. And by definition, an impulse has an area of 1 and an infinitesimal time t. So theoretically, this time here, t equals 0, or let's say approximately equal to 0, and 1 upon t, this equals infinity. Right? So it's shown as a fact column here, but in fact it's a very, very infinitesimally narrow, infinitely tall pulse, and but it still holds this property that the area under the curve is 1. Right? So that means that if we integrate between 0 and whatever time t is, the infinitesimally small time, then multiply that integral of our area 1 by 1 upon t, which is the height of the curve, then we end up with 1 by definition. So that's impulse is pretty straightforward. We don't really have to do a transform per se. We just approximate it in the time domain, and it gives us a value of 1. So as I said, as t approaches 0, if it's infinitesimally small, then amplitude becomes very large, and we define this Dirac delta impulse function. And this is how we define the impulse delta as a function of t equals 0 for all t that's not equal to 0. But when t does equal 0, so at 0 time, we get a value for this Dirac delta function. And for that moment, when t equals 0, this value is infinite. And as I said, the area, the unit area of our Dirac delta function is 1. So that's just an interesting little property of a Dirac delta, getting a little bit into the maths of it, but not too much because we're not so interested in the maths, we're interested in applying it in controls. Right, so the next thing we have to deal with, we've done a couple of examples of creating Laplace transforms. We'll look at some modeling in a bit and do some more of those. But we also have to be able to, and if I skip back to the diagram at the start of this particular lecture, we also have to be able to do the inverse Laplace transform. I showed you this, right? I showed you that we have, instead of solving the differential equations in the time domain, to get our output y, we're going to solve them using algebraic methods in Laplace domain to get our output y, a capital Y as a function of s, our operator, a Laplace s function. But then we do have to do this bit here, inverse Laplace transform, if we want to get back to our time domain. So we're looking at this now. How do we do this part, inverse Laplace? Well, the theory says that you're supposed to integrate along a contour in the S-plane, right? And we'll do a lot more with the S-plane as we go through the course. But basically, the S-plane is a complex plane. So you have a real part and an imaginary part. This is your real part sigma. Your imaginary part is omega. J omega is the imaginary part. So basically, you have some function S that has a sort of trajectory on this S-plane, and you're supposed to integrate along that trajectory, along the contour, to get your inverse Laplace transform. But that's a pretty mathematically complex way of doing it. So we have the easier route of, once we found f of s, or once we have our function of s, to get our inverse, our function, go back to the time domain, then we basically break it down, our function of s, break it down using partial fractions, and then look up or try to break it down to form of equations, or form of algebraic expressions that we're familiar with and that we can use our lookup tables to get back to. And if I open the Laplace transform tables and remind you of those again, there are different forms of these Laplace transform tables. Right, here's an example. This is one which is provided for you in your exam. So on the right hand side, here we have the s function. On the left hand side, we have the equivalent time function. Right, so let's look at the familiar one. There's some better expressions here. So we already looked at the unit step function in the time domain, is our 1 upon s in the Laplace domain. Our unit ramp function, 1 upon s squared. Our exponential with the coefficient of minus alpha t gives us 1 upon s plus alpha in the s domain. Right, so if we can get an expression that has this form, for instance, 1 upon s plus alpha, then we know that term, when we take the inverse Laplace transform, will take us back to an exponential term with the coefficient minus alpha t, right? Or if the if an alpha here is negative, then you'll get e to the plus alpha t. Now you can see there is a number of different functions here that we can use as sort of standard functions if we want to get the equivalent expression in the time domain. If we have a function that we can't break down too easily, it's got very, it's got alpha and beta as being our coefficients, our coefficients of this sort of quadratic denominator on this one, and we have an expression we can use for that as well, which ends up working out the same as this one. But okay, so basically what we said here is, instead of the mathematical solution of integrating along a contour, we're now going to break our function f of s into subfunctions and use that lookup table we just saw there. So that brings me to our first example, which we can, I could just write out. So this is a reminder of partial fractions. Hopefully you'll be pretty familiar with partial fractions, but we can express our function here, f of s, in partial fraction terms. But first of all, we might want to factorize the denominator. Well, the s to the 0 term is 6, so if that could either give us 1 and 6 or 2 and 3, but we can see that 2 and 3 would be the right numbers here. To factorize that denominator, then we state, in using partial fractions, that's equivalent to some unknown a over s plus 2 plus an unknown b over s plus 3. So that allows us then to equate the original function and our function we've broken down using partial fractions, but with unknowns a's and b. So if we cross multiply by the denominator, we get 4 equals a times s plus 3 and b times s plus 2. All right, and now we can substitute in values. Just say if s equals minus 2 first of all, then well, let's do minus 3. Then that gives us a value for yeah, okay, I did it the other way around in my notes. Okay, let's do it. S equals minus 2. That gives us a equals, oh dear, what did I do there? All right, a equals 4, right? Because if you do s equals minus 2, this goes to 0, and this goes to 1, so a equals 4. Right? And if s equals minus 3, so we're cancelling the a term now, this term is going to 0, so we're going to get minus b here, because it's minus 3 plus 2 is minus 1 times b, minus b equals 4, so then in that case b equals minus 4. And so now we can say f of s equals a, which is 4 over s plus 2, minus 4 over s plus 3. Right, now we want to get back to f of t. F of t is the inverse Laplace transform of f of s. But now we've got these terms in sort of partial fractions, we've broken it out into terms that we're familiar with. Then we can say the constant is 4 times the inverse Laplace transform of 1 upon s plus 2, and minus 4 times the inverse Laplace transform of 1 upon s plus 3. All right, and from our lookup tables, this is in the form of both of these terms here. So from lookup tables, if f of s equals 1 over s plus a, then inverse Laplace transform gives us f of t equals e to the minus at. Right? This is in our lookup tables that I just shared with you, or just showed on the screen. It's on my e-learning as well. Right? So that means that when we take the inverse Laplace transform of this first part, that's going to give us e to the minus 2t, and the second part is going to give us e to the minus 3t. I guess I could use different colors for that too. E to the minus 2t, e to the minus 3t. Therefore, our output function f of t equals 4 e to the minus 2t. Don't forget we have this constant 4 here. We have a constant minus 4 here. So it's going to be minus 4 e to the minus 3t. And that's, oops, that's what we're looking for there. All right. So we basically solved that inverse Laplace transform there. Now, I'm going to switch across to MATLAB at this point, because another thing we might want to do is to actually plot this and see what it looks like. We're going to use MATLAB here. So let's replicate what we just had. F equals, I'm going to do it in parts. So let's do the first part. F1 equals 4 times exponent minus 2 times t. Now, made a small error there because I haven't defined t yet, so just going to define t first of all. I'm going to define t as a range between 0 with steps of 0.1 up to 3 seconds, right? This is time t. So I've just created an array or a matrix of time t. You can see it appears in my workspace on the right hand side. If I double click on this, this is my time t showing up here. I just gone up in 0.1 of a second steps and created this matrix. Now I can use the equation I typed before, because I had my t as a function here as a variable, but I hadn't defined that matrix yet. So now I can create F1, and I can also create F2, and this is minus 4 times exponent minus 3 times t. All right, let's just flip back. Minus 4 times e to the minus 3t. So I've created these two. So now I'm going to create a new figure, and I'm going to plot t, F1, and I'm going to plot t, F2. I think I can do it this way. All right, so there are my two sort of parts of my response, my time response. The negative one, starting here, has got a coefficient of minus 3t, and the positive one, starting here, the plus 4 minus 2t, coming down like this. Right? To make it clearer, we're just going to turn the grid on. You can toggle the grid on a graph on and off by just typing grid in the command window. But the function, of course, combines these two, so we just plotted each individual part of the function, but we can combine them as well. I'm going to call F1 plus F2. So I've just combined those two parts, just like what I have here. F equals, this is my F1, and this is my F2. So then I can give an instruction to hold on. That means I'm plotting. I now want to plot F on top of this chart. So instead of, if I just typed plot again in the workspace, it would overwrite this figure. But I want to actually plot my next variable on the same figure. So I've typed hold on to do that. And now I'm going to plot TF. See what happens there. Right. So this is my function F. Now what you're noticing is that there's a dominant part and a less dominant part in this. They both have the same coefficient, which is, well, the coefficient is minus 2 on one and minus 2 on the other. They have the same constant of 4, one being positive, one being negative. So what we're seeing is that the positive part dominates because the overall response starts out by being positive, which means the value of the blue line, or the positive part F1, is greater than the value of the negative part F2, which is the red line here. Right, so we want, what that tells us is that if you have a higher value or higher numerical value of your exponential coefficient, it actually decays faster, right? And that means it's less, has less impact on your overall response. The orange line That's the overall response. The red line, it decays faster, it loses value faster because it has a higher negative coefficient of the exponential term. So the blue line is slightly dominant in this case, which is why the orange line goes positive before it sort of settles down. So this is just something to log and to bear in mind, because that will become important later in the course as well, that you've got one term which is more important or more dominant than the other, that ultimately defines what the shape of this response looks like. Let's come back to our Laplace transform rules. A reminder, if you have some differential term, the first derivative of a function f of t, then when you take the Laplace transform of this differentiated function or first derivative function, you get this output s times our Laplace f of s minus a constant, and that constant is the value of our function at time 0, right? The time-based value of the function. This generalizes because this is a first derivative, right? F, just the first derivative of f. But if you go to higher derivatives, in other words, n is greater than 1, then you have a set of these initial condition terms, right? So in the first derivative, you just have one initial condition term that you have to take into account. But if you go to higher derivatives, you basically have a similar looking function here, but your s term is raised to the power of n times the same f of s minus a set of initial condition terms. The most important part for us is this. This is a very important result. All of this, we sort of have to deal with this and determine in any given condition or any condition whether these terms become important or not. But this first part here, this is really important, because remember we said that this is a way of solving differential equations algebraically. And this is the reason, this condition, this property, this is why we can use Laplace to convert a system of differential equations, call them LDAs, as linear differential equations, into an algebraic problem. Now we have, our function, our Laplace transform of the function f of s times s to the power of n. So this is just like a polynomial, which we can handle a lot more easily algebraically than we can trying to solve a differential equation. So very important result. Let me rub this out now so that you can read the next part of the slide. Hopefully you got that memo before it was erased. Right, so this is the general expression, s to the power of n times our basic Laplace transform f of s. So this is we take our f of t and we just take a Laplace transform to get f of s, right? So that kind of remains untouched. But to handle the derivative, or maybe I should circle all of this, to handle the derivative, that's where we get s multiplied by s to the power of n, n being the derivative that we're dealing with. Right? But then, as I said, we have this set of initial conditions which we have to take into account. Now, because we're dealing here with the derivative, like if we were to think practically about it, this derivative could be, it could be acceleration. Right? So if we have a body that's accelerating, a equals d2x by dt squared, right? So a, acceleration, is actually a second derivative of displacement x. If we want to know the actual condition of a body that's being accelerated at a rate a, we do need to know, what was the initial condition of its position and the initial condition of its velocity. Without knowing those two, then we can't know the full behavior of that of the body, right? So I'm just using that as an example to illustrate why this part, the initial condition part, is important, and why we have to take that into account. So if we wanted to take the Laplace transform of A, in this case the acceleration of some body, then that would be s squared times f of x, because a is d2x, so x is really the function, minus, then because we're dealing with position, we have to get the initial condition. We have to go from 1 to 2 of our s values times f of 0 in this case. Right, so we'd only have, because it's just a second order, we just basically have, we'd have 2 extra terms that we'd have to add on at the end based on the initial velocity and the initial position of our body that we're looking at. Integration. So if we're taking the Laplace transform of an integral function, we looked at a derivative function. Now what about an integral function? Well, a derivative, you multiplied the Laplace transform of f of t by s. For an integral function, you multiply the Laplace transform of f of t by 1 upon s. So for integration, we divide by s. Derivative, for taking the derivative, we multiply by s. Raised to the power of n. For the integral, we divide by s. Well, that's it. That's all for that part. Final value theorem. This is another important one, because often we need to know what the, for a control system, what's the steady state condition of our system. So this is useful for determining steady state conditions, like when an input has been made to a system and it's allowed to, it's gone through its transient part, it's adjusted, it's settled down, and now it's in a steady state. That's where this limit theorem or final value theorem comes in. And the way this works is we say as time goes to infinity, so as we are dealing with a steady state condition, then if we want to find the limit of our output in the time domain, but we're resolving the problem in the S domain or in the Laplace domain, then that's the same as looking at the limit of S going to 0. So instead of time going to infinity, we're now taking S as going to 0 of our Laplace transform of our function, f of s times s. So again, we're multiplying by s to find our final value of our system's behavior. Okay, and that is true as long as the limit exists. So in other words, this works if the system itself ends up converging to a steady condition. If the system's unstable, for instance, then you find that the system goes off to infinity and it doesn't find a steady state. So as I said, final value theorem, useful for determining steady state responsive systems. So let's try it out. So this is our f of s here. And we're going to use the final value theorem to find out, well, what's the final value of this function. So this could be a function which is activated by an impulse, or this could actually be the function which is the result of, we could say f of x equals an input u times a system x right? And then we could say, well, let u be a unit step input. A unit step input is 1 upon s, and let our x be a function, which is our s squared plus s plus 2. So let's assume this, that in this case our f of s is actually the product of an input, a step input, and a function that we're interested in. So to determine our limit now, we're going to apply our final value theorem, and we'd like to know what's the time behavior of this system as time goes to infinity. And we just said that since we're dealing with a function, an s transfer function, we're going to look at the limit as s goes to 0 of s times our f of s. Right? So let's apply that. What is this when we apply it to this function f of s? So the limit of s going to 0, or let's say our time function at infinity, our steady final value of our time function, is going to be the limit as s goes to 0 of s times f of s. So you can see immediately these cancel, right? So we got our s cancels with on the numerator, which we introduced by our final value theorem. It cancels with the denominator s, which we'd introduced from our step input. And now each of these s's also goes to 0 because we're saying to find our limit, we're setting s to 0. So both of those s's go to 0. So we're left with 5 upon 2. So as time goes to infinity, the value of this function is actually going to settle down to 5 upon 2. Well, equals 2.5, right? So that's the value, that's the output as time goes to infinity of this particular function. One more rule we're going to look at is the shift theorem. And this one is useful as well because sometimes you get systems where there's a pure time delay in the system. And we have to be able to sort of account for that. So if this is our function f of t, right, you can see the shape and form of it, and it starts from time 0. But now, because we have a pure time delay, and this could be from something, or the most typical reason for a time delay is transport, like something has to move, like for instance, fluid in a pipe is a good example. Or it could be, you could be a pilot. If you were to take a human control system, you could be a pilot or a driver of a car, and this gap here, the tau, the delay, is due to reaction time, right? But more typically, we'd be dealing with a system that might be the flow of fluid in a pipe. So you open a valve at one point in the pipe, and you're measuring the pressure at another point in the pipe, and the pressure is going to stay 0 for a while after you've opened the valve because the fluid actually has to move to the point where the pressure is measured in the pipe. Right? So that's a good example of transport delay. And if our delay time is tau, as shown here, then basically whatever happens in our original behavior of our system, not drawing that very well, okay, forget that. It happens the same way, but it just happens tau seconds later, right? So this is an interesting one when you take the Laplace transform of a time delayed system. See, f equals t minus tau, so the form is exactly the same as f of t. but now we just got this lag of tau. When we take the Laplace transform of that time function, then what we get is another exponential term times, so you have the Laplace transform of the original function, but the time lag or the time delay is taken into account by this exponential here, e to the minus s tau, where tau is the value of that time delay. What that tells us is it's going to create some, some interesting effects, let's say, due to the lag. If you have a pipe, right? So we have a pipe here, and at one end of the pipe we've got a fan blowing air down the pipe, and then we have a heater. This is a heater, right? So the air is being heated. So say we have a rheostat controlling the heating function, and we apply at time t equals 0, we say the voltage on this rheostat, which is linked to a heater, which is heating the air blowing through the pipe, at some time, at time t equals 0 rather, we have a step input. This is our step input, and the voltage goes up to 10 volts. And that creates a change in the temperature of the air. So immediately, as soon as that step change happens, let's assume that there's no lag time in the heating up of this element. It immediately goes up to full voltage and to full heat. So from the time when this voltage is applied to the heater, the temperature of the air, the temperature here is T1, it immediately steps up to temperature T2. Now, if the air is moving down the pipe, this is the air at T2. Down here, your air is still at T1. So if we had, for instance, like a temperature sensor here. So here we just have a little sensor, T, right? That's not a very good drawing, but okay. This is our temperature sensor. It looks a bit phallic, doesn't it? I should probably try to adjust this a little bit. There we go. Okay, so this is our temperature here. Although we stepped up the voltage at time equals 0, obviously because this air is moving down the pipe, at time t equals 0, the temperature is still going to be 0. Right, so I'm now going to do another axis here. This is our temperature T, and it's going to remain at a lower value, which is T1, until the air reaches the sensor. So let's say at this point, okay, now the air has reached the temperature, it's stepping up, and now it's stepped up to T2. Right, so what you see here is there's a lag. This lag is called tau. It's a pure time delay between the time when a control action was executed on this system, which is the voltage was stepped from 0 to 10, right? Therefore, immediately the air in the pipe that was passing by the heater stepped up from temperature T1 to T2, but because the sensor is in a different place, is down the pipe, it took a while for this air to move, to transport down to this sensor. So the measured temperature took a while to change, right? And the time it took is actually tau. That's how long it took this air to move from the heater to the sensor. So that's just an example of a time lag system or time delayed system. And we've got a lecture on this later down in the course, so that's where we'll look at this example again. But just to give you an idea of what that means. So what that does is when you take the Laplace transform of a system that has some kind of time lag in it like that, then you take account of that when you do the Laplace transform by introducing this additional term e to the minus s tau. Okay, so coming back to the transfer functions. Transfer function, now we've got our system which is really determined by differential equations. Now it's expressed as in S terms in the Laplace form. You can actually get the transfer function of the system, and that's the output divided by the input. And when we have a transfer function, we can then sort of present our system using a block diagram, and our input multiplies by our transfer function to get our output. Well, that's pretty obvious, because if we say our output is y of s and our input is u of s and our transfer function is g of s, then as we show here, g of s equals y of s upon u of s. That means that output y equals g times u. And this is where solving these transfer functions in the S domain becomes really easy, because you can see that's just an algebraic manipulation there to get our output. So we just multiply our transfer function g by our input to get our output. Dead easy. And this is true as long as our system's dynamics are linear. So if we have a highly nonlinear system, then the transfer functions approach might not work. But with linear systems, which means you have the direct algebraic equations and the system of differential equations describing the system, then you could assume the linear relationship. So let's have a look at an actual system here. So in this system, a thermometer. This is the kind of thermometer, I don't know if, when I was a kid and my mum thought I needed to have my temperature taken, my mother would use one of these mercury type thermometers, and she'd have to shake it to reset it, like this, and then she would put it under my arm to take my temperature, or under my tongue or whatever, and the mercury inside this glass tube, would rise and give a reading. And so we're performing an experiment here, and we have the thermometer at a certain temperature. We're going to measure the temperature of the liquid, theta I. The atmospheric temperature, which the mercury was at before, is theta 0. So at the point where you immerse this thermometer into the liquid, into the beaker of liquid, you can assume that the mercury is at the atmospheric or ambient temperature of theta 0. We can assume that the temperature of the liquid is 10 degrees Celsius higher than ambient, which the mercury thermometer is at. So that then becomes like a step input, because at some instantaneous point in time, you're immersing this thermometer in liquid at a higher temperature. It's like a step input of heat into the mercury. So let's model this. And the heat flow is going to be proportional to the difference of temperature across the thermometer. So if we take heat flow, then we can say our heat flow Q of T is going to be a function of our input, which is our liquid temperature, minus our output, which is our mercury temperature, divided by some constant K, and that constant, we'll call it K1, equals the constant of thermal resistance. So that's a function of the property of the glass, basically, how the glass casing of this mercury thermometer. Right, but also we've got a relationship between heat flow and the rate of change of temperature in mercury. So we actually have another equation we can use as well. So we can say also that our heat flow causes a rise in the temperature of the mercury, and that temperature rise rate is going to be d theta out by dt, right? Times some constant, another constant K2, and that K2 is to do with the specific heat capacity of mercury. Right, so heat is being injected to the mercury, the specific heat capacity will determine how fast the temperature of that mercury rises, right? So now we have a system of equations we can use. One of these equations is the differential equation. So we can combine these because they're both different expressions for heat flow QT. So we can actually equate these equations if we want to. So let's do that first in the time with the time-based equations. Right, so if we combine the k's now, just multiply k1 by k2 and let that be an expression k. Just putting them together because they're both constants, so it's just going to end up being a number. So we multiply these out, so there's k, because that is k1 times k2. Okay, so what we're going to do now, we have the expression like this, is we can now take Laplace transforms, and we are assuming zero conditions. So right, so assuming zero initial conditions, we say input minus output equals k d theta, rate of change of our temperature, taking the plus, we have theta I as a function of s minus theta out as a function of s. So this is just transforming each of these in turn. So it's just simple function. It converts to the same function in s. This one now, if we take the Laplace transform of this one, this is going to be slightly, marginally more complex because this is the first derivative. So we learned just now that that's going to give us an s times theta out s, right? Plus theta out T0. Made it a little complex because theta and theta is the same, but this is our initial condition. But we said zero initial conditions, so that goes to zero. We're just ignoring that. Now we have a simple algebraic expression which we can rearrange, and basically if we add theta 0 to both sides, right, so that gives us theta out of s times 1 plus ks. Now what we want to get is a transfer function, output over input. So to get that, divide both sides by 1 plus ks and divide both sides by theta I. Right, so our theta out s, that's our transfer function, output temperature over input temperature, the input temperature being the liquid in the beaker, the output being the temperature of the mercury, is 1 over this 1 plus ks. And this is a typical, what you call a first order form of an equation, right? So this is a first order transfer function, 1 over 1 plus ks. Now remember, this s is kind of, it's a proxy for a derivative. So we know there's a first order derivative which is governing the behavior of this system, because we've got a single value, or s to the power of 1 if you like, in this function. So this is our transfer function, and we can draw a transfer function in a block diagram form. So the block diagram form of our system here, mercury thermometer going to a beaker of liquid at a higher temperature, is going to be shown up like this. So the temperatures in time, but we've converted it to the s domain. In our transfer function block, we have 1 plus ks, our first order transfer function, giving us our output. Well, in this case, our output in time, and s is sort of pretty much equivalent to each other, right? So that's our transfer function or block diagram of a very simple system. Now, we might want to get the time response of the system. So we have the transfer function form, output as a function of input, but what actually is our output as a function of time? Right? We know that our input as a function of time is 10. Right? It's a unit step input. So our input as a function of in the s domain, since it's a step, then that's going to be 10 upon s, right? So this is our input. We know what our transfer function is, so we can multiply input by our transfer function to give us our output. We got our input, so that means our output is going to be 10 upon s times our transfer function 1 plus ks. When we take inverse Laplace transforms of this, okay, to give us output as a function of t, we have to do inverse Laplace transform. So we're going to have to use our partial fractions. Right? And when we substitute in cross multiply, we can get values of a and b, and our value a is going to be 10. Our value of b is going to be 10k. Now we can do our inverse Laplace transform. Because we have a 10k on the top, on the denominator, we're going to divide, for this term, we're going to divide top and bottom by k. That's 10 over s plus 10 over s plus 1 upon k. You see why I did that? Because now we've got this term in the s plus a format. And we know when we have a function that has an s plus a format, then the inverse Laplace transform of that So now we can take our inverse Laplace transforms. The inverse Laplace transform of this part is just going to give us 10. 10 upon s is 10 times 1 upon s, which is 10, plus 10 times 1 over s plus a, when a is 1 upon k. So that's going to give us something in this form, 1 upon s plus alpha. Alpha in this case is 1 upon k. So we're going to have an exponential with a coefficient of minus 1 upon k t. That's e to the minus t upon k. Right, so this will be the output we get. It gives us a step. Maybe a slight error here. This should be a minus 10k minus. Yeah, thought something was going wrong here. Right, so it gives us a step of 10 minus 10 to the e to the minus t upon k. Right, and that gives us a step plus a decaying exponential. Right, so that'll be the output form. Now we still have this k as a unknown parameter here. So once you get a value for k based on an actual system, remember you've got the thermal resistance K1 and the specific heat capacity of the mercury K2 as the two elements of that unknown constant K. Once you get those got numerical values for that, then you could actually plug that in and get the actual behavior. And it will be a curve looking like this. Right? Something like this, a first order response, and any first order system, remember we said this is a first order form, the transfer function is a first order type. Any response, any first order output like this is always going to have this sort of format. Let's think about what this input and output is doing. Well, at time equals 0, right, e to the 0 is 1. Right, so at time equals 0, this exponential term is going to be 1. So you get 10 minus 10. So at time equals 0, you get 0 from your response. Right, so our input is 10, but our output at this time equals 0 is 1. Then gradually the exponential term is going to decay because it's negative. So as time increases, it's going to reduce from 1 and gradually get smaller and smaller. All right, so as time goes towards infinity, this term's getting smaller and smaller. So the system output is going to approach 10. And that's exactly what happens here. As the time increases, the system output approaches the input. Now there's a key point here. You see where the time is 1 upon k. Well, what happens there? When time is 1 upon k, then this term here, this term is going to be, let's do it this way, equals 10 minus 10 e to the minus 1, right? And that e to the minus 1 is 0.32 or so. And so when you multiply it by the 10, that's going to be 3.2. Yeah, something like that, I think. So you basically, whenever you have a first order system and the time is equal to 1 upon the time constant, this fellow, the A, is the time constant. Whenever you have a time that's equal to your alpha or your A term here in the first order type system, then you're going to have a fixed output as a proportion of the input. And that output is basically 63% of your final value. Right? So that's a special condition where tau, or time, equals 1 upon k. and we call that time that it takes to get there the time constant. And so the time constant of this system is 1 upon k. So a first order system is defined or characterized by its time constant. This is our next example, and we're going to take the inverse Laplace transform of this function. So when we factorize, we first of all get 5s plus 1 over, well, 12, 4 and 3. 4 times 3 is 12. But this is minus 12, so you got 1 negative, 1 positive. So, okay, you're going to have s minus plus 3 and s minus 4 here. So this is equivalent now to a, I'm going to do it this way around, s minus 4 and b over s plus 3. So if we equate, if we cross multiply by the denominator in this case, 5s plus 1 is going to be equal to a into s plus 3 plus b into s plus 4. So set s equals minus 4 gives us 21 on the left hand side, and b gets cancelled out. So that gives us a equals 3. And if we set s equals, oops, it should be minus 4. And this should be 4. 21. This is plus 7. No, same difference. Okay, and so this is going to be minus 3 now. 5 3 is 15, plus 1 is 14. Minus 14 equals minus 7b now. So b is looking like 2. So now we can say y of s equals 3 over s minus 4 plus b over s plus 3. If we now want to get y of t, which is the inverse Laplace transform of y of s, it's going to be the inverse Laplace transform. Let's bring the 3 outside, the constant outside, 1 over s minus 4, and b is 2 here. 2 times 1 over s plus inverse Laplace transform s plus 1 over s plus 3. So we know these fellas from the tables is going to be e plus 4t. This is going to be e minus 3t. Okay, so that gives us 3e plus 4t plus 2e minus 3t. That's it. This is modeling a simple circuit, an RC circuit. Right, so we have a voltage on the left-hand side, VI, input voltage, and we've got an output voltage across the resistor. So we want to know what's the transfer function between our output and our input. A capacitor that would be the voltage across a capacitor as a function of time is 1 upon C integral I dt. So how are we going to do with this one? First of all, apply KVL, and you could also apply KCL, right? You know Kirchhoff, right? Kirchhoff's voltage law and Kirchhoff's current law. Kirchhoff's voltage law says that the sum of voltages around a closed circuit equals 0, and Kirchhoff's current law says that the current flowing through each element in a circuit is the same. Right, so you're going to apply these two laws. You can start with Kirchhoff's voltage law and just write out Kirchhoff's voltage law for this circuit. So simply, without having to actually substitute in the actual equation for the capacitance or whatever, or the resistance, you could say, the voltage across here is VR, VC, voltage across here is VR. So that means that, you could write it as Vin minus Vc minus VR equals 0. The sum of all the voltages equals 0, which means Vin equals Vc plus VR. Basically, whatever your input generating voltage is going to drop across your capacitor, it's going to drop again across your resistor and come back around to 0, right? So this is number 1, Kirchhoff's voltage law. But we also have Ohm's law, which we can apply across here, across the resistor. So now, using Ohm's law, VR, V equals what? IR times R, right? And then Kirchhoff's current law tells us the current in every element is the same. So we know IC is going to be the same as IR. So now we basically have kind of got 3 equations really. Let's say 3 is Ohm's law. This is 3. So we have, we've got 3. We've got 1 here, 2 here, 3 here. So you have 3 equations you can put together to try to create a transfer function for this circuit. So let's have a look at this. So let's just recap what we found on the last slide. So the first thing is that, I'm not going to redraw it, but we said Vn equals drop across a capacitor and the drop across the resistor, right? Using this one here. And we also said, using Ohm's law, I think next we use the current law. We said the current through the resistor is going to be the same as the current through the capacitor. And then Ohm's law, we said that the voltage across the resistor is the current through the resistor times the resistance. Then I'd also given you this equation for the capacitance voltage. Vc equals 1 upon C integral of IC dt. Now here's the little trick. If we drop all those components into equation 1, Right? Now, we have a problem with an integral, but we can use a little trick by differentiating. We can do it this way by differentiating. There are two ways we could go. We could either say, okay, let's go straight and take Laplace, or we could say differentiate and then take Laplace. Let's go with let's forget this, let's take the differentiation route and then take Laplace. My apologies. So we're going to go that way. So if we differentiate this equation now, we're going to leave this here as VR. All right. So instead of substituting in yet IR, we're going to leave this as VR, and now we're going to differentiate. So we're differentiating. So we're taking the first differential of our input. This allows us, if we differentiate our capacitor expression, then we just end up with 1 upon C times IC, because we've eliminated the integral. And then we're going to take the first derivative of R. IC is the same as IR. IC equals VR upon R. So we can substitute that in here. 1 upon C times VR upon R. I just missed this step when I was looking at my notes and kind of got a little bit lost. But I've got it back now. Right, so now we've got our expression. To remember, we're looking to get our output, which is our VR as a function of our input V in. V output is the same as VR as a function of our input V in. So this is the function we want. So now we've got, we kind of got rid of our IC, which is a parameter or a variable we didn't need. And so we are that one step closer. Right, so writing it a little bit more concisely, you get 1 upon RC times VR plus V dot R. And then we're just going to get rid of the R's and just put in outs instead, because it's really the output that we're looking for. So now we can do our Laplace transform. So now we can take our Laplace. We could have, like I said, we could have done the Laplace earlier, but it just would have taken an extra step. So this is probably the better way to go. Now, if we take Laplace of V dot in, because it's a first derivative, that's going to give us S times V in of S. V out is going to be V out of S, and V dot out is going to be S times V out of S. Of course, we're applying the Laplace transform rule, which says that d n of f d over dt to the n is going to be S times f of S plus a set of initial conditions. Right. And then I won't write the name, but we have a set of initial conditions. So we're just applying this here. All right. So where we have a first derivative, we get an S, we get another one here. So we're just going to assume initial conditions are 0. So basically that's assuming the system is at rest before we do this modeling work, right? So now we can kind of combine terms and we can get our overall transfer function. We want to get our output over our input to get a transfer function expression. So we're going to combine our V outs So if we put these together, we get S plus 1 upon RC. We can cross multiply because we also have an S on this side, of course. So we're going to take to get our V in over V out. We're going to take this fella, divide it down on this side. So we end up with RCS over RCS plus 1. Right? So just multiply up this. So if we bring the RC, multiply RC over RC for both sides, you end up with RCS over 1 plus RCS here, right? So that's how we ended up with the V out over V in equals RCS over RCS plus 1. Now this is another type of system, and this would be first order type 1, what's called a first order type 1 system. And that has a slightly different characteristic to the basic first order that we saw with the thermometer, putting the thermometer into the liquid. So we kind of reached the end of the Laplace transform part, and we started getting into mathematical modeling, with those, especially those two examples of the thermometer, the mercury thermometer into the liquid, and then secondly that RC circuit, resistance and capacitor circuit. That firstly we said dynamic behavior is described by differential equations and by a system of differential equations for most systems. And once those differential equations are linear, even if they're higher order, it doesn't have to just be a first order differential, it could be a higher order differential equation that's determining the behavior of the system. If they're linear, then you can solve them more easily by taking Laplace transforms, right? And getting the time-based response of these systems. And they also allow us to use like standard tables to get those Laplace transforms. We can, once we get it into Laplace form, apart from the fact that it becomes easier to solve because it's now an algebraic manipulation, basically, or an algebraic rearrangement. The other important thing is that we have different types of systems and controls. We have electrical systems, we have electronics, and we also have sort of mechanical, fluid, thermal systems. So all these different types of systems are integrated into a control system, and we want to be able to solve it as one integrated system. And that's why, another reason why it's much better to put it into the Laplace form, because then, we get away from, able to solve it together as an algebraic expression, regardless of the different domains that we're dealing with, different physics domains, if you like, that we're dealing with. And then we have to, if we want to get back to our sort of time response, we do the inverse Laplace transform, and we do that by kind of rearranging our overall output function, our Laplace output function, and using partial fractions we can break it down to standard elements, and then we can sort of use the tables to get the inverse Laplace transform of each of those standard elements. And therefore, we can get the overall time response of the system. So that is Laplace.